Section 11.5, Polar Bonds and Molecules. This is a supplementary section to the textbook. Here's our objectives here. How do electronegativity values determine the charge distribution in a polar bond? What happens to polar molecules between a pair of oppositely charged metal plates? How do intermolecular attractions compare with ionic and covalent bonds? And why do network solids have high melting points? So, when we get done, check back, see if you can answer all of these. Let's talk first about bond polarity. And if you have two atoms bonded together, they're going to pull on the electrons. And if they pull with an equal amount, if they're exactly even, then you have a nonpolar covalent bond. So one of them doesn't get the bond a little bit more than the other one. So let's take a look at some examples of that. And if you have just like hydrogen, and you've got its one electron, you've got another hydrogen, its one electron, these two are being shared. So these electrons are going to go around here this whole time. And if they're even, if both hydrogens are exactly the same, which hydrogens are, then they're going to be shared exactly evenly. Same thing for oxygen. You get two oxygen molecules and they're going to share evenly, and so on. In other molecules, in other bonds, they're not shared evenly. And when that happens, you get a polar covalent bond. That's where one atom is more electronegative. It's going to pull the electron in more than the other one, and then you get a slight charge. So for instance, if you have hydrochloric acid, HCl, the chlorine is much more electronegative than the hydrogen is, and so it's going to get a negative charge, slightly negative charge. And we usually indicate that with this funny looking delta sign. I think it's like the small letter for the triangle one. So you've got a delta plus and a delta minus. So the delta plus means that that electron isn't there as often as it is on the other side. And another way that they write it, sometimes they write it like this, where they use an arrow and they put the plus sign over the positive side and the arrow points to the negative side. Now you can also have a molecule which is polar. In other words, it has one end which is positive and one end which is negative. And if that happens, then you get a molecule that has a charge. It's known as a dipole, and it can be put in a field where you've got, positive charges and negative charges, and it will line up in such a way that the positives will be towards the negative side and the negatives will be towards the positive side. Okay, that's what they're talking about when they're talking about a dipole. It's a molecule in which you have a positive or negative side. All right, let's talk about some attractions that occur between molecules. And there are three kinds. These are all weak. They're not as strong as covalent, certainly not as strong as ionic, which is stronger than covalent. But there are three of them. But they do determine whether a substance is going to be a solid, liquid, or gas at room temperature. So they do have some influence in some of these things. The first two are known as van der Waals forces. The two weakest ones are called van der Waals forces. And the first example is a dipole interaction. And this is where you simply have polar molecules and they're attracted to each other. So you've got like a positive and negative side, and it's going to meet up another one that's positive, negative, and those things are going to be, there's going to be some attraction between those positive and negative ends. It's not very strong. It's going to be, pretty weak, but it's similar to the idea of an ionic bond, just much, much weaker. So that's known as van der Waals forces. The other one, the next one, is called dispersion forces, and this is the weakest of all of them. And this is simply caused by the motion of electrons. So if you've got your nucleus and you've got these electrons moving around here, as they move, they cause this movement, causes an attraction between other atoms. That's known as dispersion forces. The more electrons you have, the more dispersion forces you have. Now these will occur even in non-polar molecules. You don't have to be polar to have dispersion forces. And the halogen's probably the best example, because if you think about it, your first two are fluorine and chlorine, and those are gases. And as you get bigger, as you add more levels, more electrons, so there's more movement, you get bromine, which is a liquid. And then you have iodine and astatine, which are solids. So as you add more electrons, they get to be, their state changes. All right, the third one is known as hydrogen bond, and this is the most powerful of the three. And it's where, in order for this to happen, you have to have a highly electronegative atom bonded to hydrogen. Have to have hydrogen involved here. And so a good example of that is water, because water has had hydrogen and oxygen is electronegative. And so what happens is the oxygen gets to be negatively charged, the hydrogens become positively charged, and then as they meet other ones, there's other water molecules, they're that same thing. And so now you've got a bond between these two. So it's very similar to what we were talking about in dipole interactions there. But it's stronger because when you have hydrogen, if you take that electron away, all that's left is a proton, and that's stronger. It's just, positive charge attracting the negative electrons. So hydrogen bonds are the strongest of the three. They're about 5% of a covalent bond. So you can see they're still weak, but comparatively they're quite a bit stronger than the other ones. And it's why water is a liquid at room temperature. Most things that are that small, have that small molecules as water does, at room temperature they're usually gases. Propane would be, or methane actually would be better, would be a good example of something about similar size, but it's a gas. Ammonia is gas at room temperature. On the other hand, hydrogen or water, because of hydrogen bonding, tends to be a liquid at room temperature. So of the three, this is the strongest one. Okay, let's finish up here with network solids. And a network solid is a covalently bonded compound where all of the atoms are bonded. It's just like one big continuous chain. If you look at this picture on the right, which is supposed to be a diagram of carbon bonded in there, so that's diamond. And these molecules are so strong and they're so hard to break, these bonds, that they have very, very high melting points, even higher than ionic ones. So sometimes in the thousands of degrees. And they don't usually melt, they just decompose. So they go from being a solid to gas. These are known as network solids. And so in order to break these bonds, you have to break them all in order to melt it. And so that's right, it's really hard. A couple of good examples, and you should know these, would be diamond, quartz, and silicon carbide.